Welcome to chapter 6. This chapter deals with recursion. The first problem asks us to use recursion to count the number of vowels in a string. Here's a demo. Apple contains two vowels, A and E. Note that both vowels are in different cases. None has no vowels. So let's go through the code. If not S, return 0. So if S was an empty string or if S was none, then we'd return 0. If not, count the number of vowels in S starting from the second character. If the first character was a vowel, add 1. If not, just return the number of vowels in rest of S. That's the code for this problem. The third question asks us to fix the program, but here is a lot cleaner way to write the code. So consonants are basically non-vowels. So in Apple, P, P and L should be counted as consonants, and as far as none is concerned or an empty string is concerned, they have 0 consonants. As seen in the previous problem, we addressed both none and an empty string through this block of code, and we use the same check. If it is a vowel, then we return the number in rest. If it is a non-vowel, then we add 1. Here's the output. For Apple, there are 3 consonants, and as far as none is concerned, 0 is the correct answer. Welcome to 4a. We are asked to print the first n terms of geometric progression. So if n is 0, we don't print anything. A geometric progression is of form a times r power n, where n refers to the nth term. So we get the user input here as shown here, and we print a bunch of comma separated items. So if n was 0, we have nothing to print, so return. So depending upon whether we are printing the last element or not, we decide whether we want to have comma as the end separator or we just want to have a blank string. If we have reached the end of recursion, we just print a new line, which is what brings our cursor to the next line, and return. And since we start iterating from the first term, we keep incrementing so far by 1 to check end of recursion. Let's look at problem 4b. Here we are supposed to print the sum of the terms of GP. So here we have the terms of geometric progression, and if we sum these, we'll get 80. That's what is shown here as part of the demo. One thing that you'll notice here is that here we have just 3 parameters instead of 4, which contains so far. The reason for having just 3 instead of 4 is because when we had 4, we were able to print the series in increasing order of n. But when computing the sum, the order of iteration does not matter. So we can go from back all the way to the front, and we'll still end up getting the same result. Welcome to the fifth question. We're asked to print the number of digits in a number. So here's how we do it using recursion. If n is less than 0, then we take the absolute value, so our n becomes positive. Now if n is less than 10, there is only 1 digit. If not, we count the number of digits in the quotient where n is divided by 10. That's going to give us a remaining number of digits. So if we had 123, dividing by 10 is now going to give us 12. Count the number of digits there recursively, and then return 1 plus the remaining number of digits. So here's the output. 1 has 1 digit, 10 has 2, 100 has 3, and minus 102 also has 3 digits. Now that you folks are familiar with recursion, the sixth one should be plum. We're asked to find the maximum of a list. So first up, we'll make a simplifying assumption that the list should be non-empty. So that's why we have an assert here. So if the list has just one element, then the element at 0th index is the maximum. If not, you find the maximum in the rest of the list, and then you use the built-in Python function to find the maximum between the very first element and the rest of the list. So 1 here is a trivial solution. In 2, 1 and 5, 5 is the maximum. Let's turn our attention to a problem that's covered in your theory textbook, which is to compute a power b. The requirements are A and B should be non-negative, and this is the brain of the program. If B is less than or equal to 0, you return 1, else you return A times power internal of A comma B minus 1. Odds are good that you're asked to get rid of this condition and make this program run faster. Currently, the runtime is linear in terms of B because every time you're reducing B by 1. So let's see how to do both. First up, here's the output of the fixed program. We'll see here that for non-negative powers of 0, we get the correct output. From then on, we see that up to section here, that no matter the sign of the base and the exponent, we'll get the right value. If you consider minus 2 power minus 2, it's actually 1 divided by minus 2 the whole square. So you'll have 0.25. This is also correct. You can verify results up to this. In fact, up to this by yourself. And finally, we catch the case where result is undefined for 0 power minus 1. So that's what this main does. And let's see how this gets done. As far as improving the first condition, that is for both A and B to be non-negative is concerned, we have changed it to the case where when A is 0, B should not be negative. So that part is done. Now let's look at the second portion as to how we are improving to a sublinear time. So here, when exponent is 0, you return 1. When exponent is 1, you return base. Those are the base cases. Now here comes the interesting part. Every time you compute half the power, that is, you compute A power exponent divided by 2, that is the quotient of it, and you check if exponent is a multiple of 2. If so, if you multiply half the power twice, you get it to the power of B. If not, you multiply this, that is the result of multiplying 2 half powers along with the base to compute the odd power, and eventually you return the result. If you analyze the complexity, you'll notice that say if it was 8, you'll compute the power internal of 4, then you'll compute power internal of 2. So the complexity now is now reduced from a linear to a logarithmic time. The final snippet of interest to us is this one. So when you compute A power minus B, it is just the reciprocal of the power. So you compute the power, the result as always. You provide B as the absolute value so that B is always non-negative. And if B was less than 0, that is the exponent was less than 0, then you return the reciprocal of the result computed. This makes our program more flexible and robust as well.